So yeah, in the actual project in which we work, or me and Martin Gaia, is again the CRC, yeah, this TRR 277, and in this project we'll investigate different methods for 3D printing for houses and buildings. So, and this video you can see this 3D shotcrete 3D printing process. Yeah, you have some robot and which applies this 3D this shotcrete jet on the earth surface and printed some shapes, some for building, and this process. And this process we want to modulate and simulate with the VirtualFluids actually. So, and as you can see, this part, what we want to simulate, actually this part of this process, yeah, the nozzle itself and this jet, shotcrete jet, is a high turbulent flow, multi-phase, because we have in concrete, yeah, in this shotcrete jet we have two fluids actually. Two fluids phases, water and fresh cement paste, and solid fraction, some particles, additives, yeah. And it's high turbulent flow with high density ratio, because we have water and we have surrounded air. Yeah, this fresh concrete, not water, fresh concrete fluid and surrounded air. So and particles, some solid particles. Yeah. So, and these three components which we need actually to model in this concrete 3D printing process. First, we need non-Newtonian flow for fresh concrete, then coupling, some DM coupling, discrete element methods for modeling particle. Yeah, we don't want to implement this particle self. Yeah, we can take some framework for this and couple, and multi-phase flow to simulate this fresh concrete in air. So yeah, okay, and this it was implementation of non-Newtonian fluid. We evaluated our implementation with this benchmark, actually plug flow between two cylinders, which actually typical used in some rheometers, for Newtonian fluids, and here you can see, and if you have non-Newtonian fluid, you have the typical so-called plug flow, which with Newtonian, if you have Newtonian fluid, you have here the parabol typical, and for non-Newtonian fluid, we have this characteristical shape of
it moves like a solid.
Yeah, it moves like a solid. As this plug flow means that for this this x axis is rotation, no. This position is radius, yeah, and this is rotation speed, velocity. And you can see, yeah, this if we close to the cylinder, the outer cylinder, yeah, is more. It's like a solid with this. Then we have constant velocity. Yeah, angular velocity. Yeah. So okay, and we compare this to analytical solution. Yeah, it's pretty good match analytical solution zone. So and here some so simulation. Yeah, this 3D printing process. How is called?
Strong deposition.
Yeah, this the deposition of some non-Newtonian the concrete, we can say, yes, like concrete, the fluid like fresh concrete. So then we also use lights framework, this discrete element method, to simulate the particle and couple this with VirtualFluids, evaluate this with a benchmark is fallen sphere, and it's also very good match analytical solution. So, and here video, yeah, is simple. Okay, in this case, single phase flow, and this is geometry for shotcrete nozzle and the flow inside nozzle. Yeah, we want to see, okay, what happens with particle inside nozzle, and here's the particle which created with this framework, and interrogate with the flow. Yeah, and this it was implemented, this coupling with our solver, the two solvers coupling principle. So then next we for multi-phase flow we implemented, yeah, we tried different models, and then for this case, for higher density ratio, so like 1000, we developed special model, sharp interface model, yeah, and which very good approximate this high density ratio. Okay, I don't want goes into details. Just again, we evaluate this with rising bubble. Yeah, 2D. It was, yeah, this we has you have a gas bubble surrounded the liquid. Yeah, some heavy liquid, and we have here gravity, and there is some analytical solution. In this case, yeah, this should be go up this bubble, and it's the bubble have a special the specific shape, and the on the top if goes up, and here rise velocity of this bubble. Yeah, and this more or less also match other simulations. So with other methods, yeah, with other methods for this case. So, and here practical simulation as other benchmark. We don't have analytical solution for this, but we can see, yeah, so it's more or less correct behavior, physical behavior for jet breakup. Yeah, it's, this is a okay. In next, okay, last slide is simulation. This shotcrete jet. Yeah, again, as this is nozzle geometry and this multi-phase model. Okay, but without this particle, that we could solve the problem. Yeah, the couple particle with multi-phase. Like, they don't solved. So, but you can see it's also yeah, pretty similar to the yeah, what we see in the video, and we also compute. I don't have the slide, I think. Yeah, we compute average velocity of in the jet. Yeah. This. Here in this part, and we applying some like yeah, we have the high resolution video of the jet, of the experiment one, and apply, how it's called,
particle image velocity.
Yeah, particle image velocity, velocimetry methods to investigate this average velocity in the experiment. Okay, because our project partners, they only, yeah, they experimented only this, how good jet or how good concrete applied on the surface. Yeah, doesn't care about this. Yeah, about average velocity or something like this. But for us, this was important, of course, important parameter to compare our simulation. Yeah, and
if you ask these people how to, sorry.
Yeah, you can explain.
Basically, you could think, I mean, civil engineers, so how fast does this come out? So they take a bucket, yeah, and they fill up the bucket, and it takes so long to fill up the bucket, so there's the velocity that it comes out.
Yes, but okay, but yeah, with this methods we can compare it, and it was yeah, pretty close to the experimental. Our average velocity in velocity profile was very close to the experimental one. It was very, yeah, satisfied.
What you showed before, that was the breakup of the single bubble, right?
Yes.
There was a comparison between different
yes, it was
literature and which one was your own?
Yes, sharp interface is on.
The diffuse was also.
Diffuse interface is also our implementation, but the problem with diffuse interface was that cannot be stable with this high density ratio.
No, with this low viscosity.
And low viscosity, yeah. High density ratio.
Both.
I mean, no,
yeah. If you combine both.
Yeah, if you combine both, yeah.
Because they have to have high density ratio and low viscosity.
Yeah, it's the problem actually. So.
And then what we see here, right? That's just how the bubble is breaking up into droplets, right? Or kind of.
Yes. Yeah. In some simulation, you can see the separations. Yeah. And other not, yeah, but here two classes of methods, yeah.
You actually see this better in the other problem.
Yeah, genau, other side.
In general, there's the diffuse interface models. They come out with a lower velocity in the end. And the sharp interface models, they come out with a higher velocity at the end.
And it's comparable to other simulation with the same same method concept, we can say.
Yeah, so right, so the diffuse interface models have one result and the sharp interface models have one result.
Okay.
Yeah?
So, okay.
Question to the last, like this plot.
Yeah.
Why don't the drops achieve arrive at the wall? Or like it looks like zero gravity.
No, they go back, there is gravity.
Here. This.
No, like where it was.
Yes, there's no gravity.
Okay, with here, with short grid. Yeah, yes, it's without gravity. Yeah, you're right. Yeah, it's without gravity. It's
Why?
Because it's too short.
Yeah, it's too short and too high velocity. Yeah.
Okay, so yes, you can add gravity, but that doesn't.
Yeah, if you look
the
at
idea behind shotcrete is that you take the hose and you could actually shotcrete to the ceiling if you want, like, yeah. So the idea is that the shotcrete is so fast that gravity doesn't play a role.
Yeah, it's you can see. Yeah, it's now the vertical wall for it. Yeah, here. Yeah, it's simple.
So the advantage would be to be faster in building something.
Not only, but also create some crazy shapes. We can say it's not.
No, because if you. So most of the 3D printing of concrete is just the positioning, what we've also seen, and they only print according to gravity. So this can print against gravity.
In all direction. Yeah.
Shotcrete is not a new invention. It has been like for a long time. Basically, in tunnels, where you
They print to the ceiling.
you want to pour concrete, but how you would do this in the ceiling? I mean, you're underground, so you simply put the grid of reinforcement and shotcrete. That's it.
It's pretty cool.
So okay. And I think this last, yeah. Okay, in this, last slide. As of now, we're working on, we can say some fluid structure interaction, no 1K couplet. Yes, it means, motivation is other 3D concrete printing methods, call it injection 3D concrete printing. Idea is you have some carrier fluid, and you print inside this fluid, then again you work against gravity, something like this, you don't depend on gravity, okay. So and here we try to model this. Here this printed head or nozzle, and so and some printed try to print some strand, single strand.
Okay, I mean so it is obvious now that this is not actually the physical result that you later have. So this is the thing under development. Of course this doesn't look like this in reality.
Yes. It's what we're working now, actually. So okay, I just make a cut.